Now let's look at complex fractions. There's one correction I need you to help me make. We are not solving, we are simplifying. So let's make that change. Simplify the following using both methods. The idea here is for complex fractions, we have steps that we can follow, mathematical procedures. Some may call them algorithms that help us to simplify problems. And you'll find that there are multiple ways to approach a problem. Here for complex fractions, we have two methods that summarize these procedures that we can use. And I'll be demonstrating each of them for the same problem so that we'll be able to compare the different steps and notice that no matter which method we use, because they're both mathematically correct, we will end up with the same simplification. So instead of reading through the procedures up there, I'm going to try to show them to you step by step. So let's take a look at the first problem. Xy squared over 9 divided by x squared over 3. Big picture with complex fractions is they're really a fraction with fractions inside. That's why they're called complex. So for method 1, the first step in method 1 is to simplify the numerator and simplify the denominator so that you end up with one fraction in the numerator and one fraction in the denominator. And we have that already in this problem, so step 1 we don't have to do. Step 2 says to take this problem, xy squared over 9 divided by x squared plus 3. I'm going to write it as a division problem, noticing that this large fraction bar here is really division. Once we do that, we can copy, dot, flip. We copy the first one over as is, we change the division to multiplication, and then we take the reciprocal of the second fraction in order to turn the division problem into a multiplication problem. Once we do that, we can multiply like we multiplied rational expressions before. We don't just want to multiply straight across though. We want to make sure that we cancel common factors so we don't have to do it later. So I notice that I've got a 3 and a 9, so I can divide by 3. I also notice I have an x in a numerator and an x in a denominator, so I can cancel those x's. And in doing that, the only thing remaining on the numerators is a y squared, and in the denominator we have a 3x. That's our solution. Let's compare to that how method 2 would work. So in method 2, we look at all the fractions that exist in the problem, and we find the LCD of all the fractions. So before I do that though, I'm going to copy over the problem. xy squared over 9 divided by x squared over 3. I need an LCD, and I'm looking at denominators in the problem. All the denominators, top and bottom. And I notice 9 and 3, my least common denominator is 9. Remember, I have to have both numbers divide the least common denominator. 9 divides 9 and 3 divides 9. So my least common denominator is 9. I'm going to multiply this complex fraction by a special form of 1. And that special form of 1 is going to be my least common denominator, 9 over 9. Let's see what happens when we do this. So xy squared over 9 times 9. X squared over 3 times 9. I can cancel common factors. 9s will cancel. 3 cancels with 9 and leaves behind a 3. On the numerator, all I have left is xy squared. In the denominator, I have 3x squared. And I take one quick check. Do I have anything in here that will cancel? And I do. I can cancel an x top and bottom. And we're left with y squared over 3x. Oh wait, that is the exact same simplification we got before. It should be the case. We should get the exact same answer both times. Let's take a look at the next problem. A little more complicated. Now we don't just have one term in the top and one term in the bottom, we've got two. So now we need to use that first step in method 1, where we're going to treat these, we'll treat what's in the numerator as a problem, and then we'll treat what's in the denominator as a separate problem, and then we copy dot flip, turn it into a multiplication problem, and simplify it. So looking at the numerator, 4 plus 2 over x. I need to think of a least common denominator here. I only have one fraction, so my least common denominator is that denominator. I'm going to scoot my 4 over a little bit so I can force some room in here. I need to multiply 4 by a special form of 1, so I get a common denominator with 2 over x. I'm going to multiply by x. 4x over x plus 2 over x. I'm going to kind of pretty much ignore my denominator for now and just focus on the numerator. Now that I have a common denominator x, I can combine my numerator, 4x plus 2. And then I can't really do anything else beyond that. I need to go back and work on my denominator. So we've got 1 minus 3 over x. We can play that same game. New least common denominator here. I only have one fraction. It's an x. So I need to multiply by that special form of 1, x over x. So we end up with x over x minus 3 over x. I have that same denominator. So now I can combine numerators, x minus 3. And I end up with a complex fraction, one term on the top and one term on the bottom. And notice by term I'm saying term. And now that I have one term over one term, I can turn this complex fraction into a division problem. 4x plus 2 over x divided by x minus 3 over x. And then I copy, dot, flip. I've got a multiplication problem. Now I can cancel common factors. I notice up here I've got a 2 that's a common factor, 2 that's a common factor, so 2x plus 1 does not cancel with x minus 3, so factoring didn't really help me simplify it anymore. 4x plus 2 over x minus 3. So that's method 1. Let's take a look at method 2. Method 2 says first find the least common denominator of every single fraction present in the problem. That LCD is going to be x. We kind of saw it here in method 1 as well. So we multiply the entire problem. Notice instead of focusing on the numerator and then the denominator, we just go ahead and multiply the entire problem by our least common denominator special form of 1. And when we do that, remember we are distributing that special form of 1. We're multiplying by the whole thing. Let's distribute. I'm going to write one more step so we can really see it. So 4 plus 2 over x times x, and 1 minus 3 over x times x. So here's that special form of 1 now in the same fraction, the same complex fraction. And now I can distribute 4x plus 2 over x times x, 1x minus 3 over x times x. And if there's anything we can cancel, yes, x's. And on the top, 4x plus 2. On the bottom, x minus 3, which is exactly like what we got before, which it should be. In this situation with more than one term, method 2 tends to be a little faster. You have fewer steps that you have to deal with, but big picture, you can choose which one you like better. The only thing I ask is that on this worksheet, you do both method 1 and method 2 for every problem. And then when you're in the homework, try to do all of the odd problems with method 1 and all of the even problems with method 2 before you really make a decision. This is the method I like and this is the method I want to do. But don't stress yourself out over one particular method if it's just too much and you like the other method. I am not going to ask you on a test to show me both methods. I just want you to be able to know one. So practice both of them before making a decision on which one you really like to do. It's always good to practice. We should always be practicing so that we can learn. And then on the next page, there's another problem. I'm going to leave number 3 for you to do on your own. Let's take a look at number 4. So just like before, method 1 says we're going to treat the numerator as a problem and the denominator as a problem, and then we'll put them together. So in the numerator, 9 over x plus 3 over x squared, we need to consider a least common denominator. And x squared, our LCD should be x squared, so we can multiply by a special form of 1 so that we end up with the same denominators in the numerator of this complex fraction. And so first term, 9 over x, I need another x. So let's go with that. 9x over x squared plus 3 over x squared. Now that they have the same denominator, we can write the numerators together, 9x plus 3. And we could factor here or not. It doesn't matter at this point, but I see the 3 is a common factor, so I'm going to go ahead and factor that 3 out before I go back and look at my denominator. So I've got my numerator as simplified as I can get it. Let's look at our denominator now. 3 plus 1 over x. LCD for the denominator, I only have one denominator, it's x. So I still need to multiply the 3 by that special form of 1, x over x. And we end up in the denominator, 3x over x plus 1 over x. I have the same denominator here, 3x plus 1. I can't factor anything out, so I'm just going to go ahead and write it over here. 3x plus 1 over x. And now we change this big division problem into a regular division problem and then a multiplication problem. 3x plus 1, x plus 1 over x squared divided by 3x plus 1 over x. Tiny little bit of shifting around. And then we copy, dot, flip, and we can cancel common factors. 3x plus 1 will cancel. The 1x on top cancels with 1x on the bottom. And straight across 3. And on the bottom, x. That's our answer. Comparing this to method 2, instead of having to separate the numerator and the denominator and finding the LCD twice, for method 2, we find the LCD only once, but we look at the least common denominator for all of the denominators in the problem. So writing this out a little bit differently, the least common denominator of x, x squared, and x is going to be x squared. So I'll write out my problem, 9x plus 3 over x squared, all over 3 plus 1 over x. I need to take that complex fraction, multiply it by a special form of 1, and that special form of 1, x squared over x squared. We're going to distribute that into the terms of the problem. So 9 over x. I'm going to write it one different way first. I'm going to change that for a second. Instead of distributing, let's write it over one fraction. So 9 over x plus 3 over x squared times x squared. 3 plus 1 over x times x squared. And now we can see the distribution that needs to happen. 9 over x times x squared plus 3 over x squared times x squared over 3 times x squared plus 1 over x times x squared. And a lot of x's to cancel. 1x with 1x, x squared with x squared, nothing in the next one, 1x with 1x. The big picture is all of those denominators should be eliminated in this simplification step. And on the top we have 9x plus 3, and on the bottom 3x squared plus x. We're not done though. We need to factor and see if we can simplify anything else. 3 will factor out, greatest common factor, and then in the denominator x will factor out, greatest common factor. And it's okay to pause the video as you determine the factoring part, or at any step. You can pause, you can rewind, you can watch again. It's okay not to get it right away. Cancel common factors, and we end up with 3 over x, just like method 1, which we should. In the last part of our video, let's take a look at an application, specifically a physics application, with light bulbs. Pictured here is part of a circuit where 2 light bulbs are wired in what is known as parallel. If 2 light bulbs are wired in parallel, if one of the light bulbs goes out, if it dies, then the circuit is not broken. The circuit will still continue. So for example, light bulb S, I've labeled them here S and T, but I'm labeling actually their resistance. But if this bottom light bulb goes out, then the electricity will still flow into the upper light bulb and allow our circuit to still be complete. In contrast, there are light bulbs that can be wired in series, which means we've got a light bulb and then another light bulb. Electricity comes in, goes through the first light bulb, goes through the second light bulb, and goes out, goes back around to complete our circuit. But if one of the light bulbs is out, then that circuit, the electrons stop. They can't go anywhere. So nothing happens and my next light bulb does not light up. It doesn't matter if it's the first light bulb that's out or the second light bulb. When the electricity gets there and the light bulb's out, it cannot go through the light bulb or around the light bulb to complete the circuit. Christmas lights are wired in parallel like this picture, so that if you lose one light on the tree, your entire string of lights is not completely dead. You still have a string of lights that work. You may just have one bulb that's out. So we have this expression for the resistance in the circuit. And if you want to know more about electromagnetism and circuit design, current and voltage and resistance, by all means, seek out those physics classes. First, we want to simplify the complex fraction. So we're given this complex fraction resistance in ohms. R is 1 over T plus 1 over S. And in my picture, I've just labeled one of the light bulbs as resistant T, the other light bulb has resistant S. And we can simplify the complex fraction. I'm going to do it down here in the bottom because I have more room, and then we'll do part B. So for part A, 1 over T plus 1 over S. You can use either method to simplify the complex fraction. I'm going to use method 2. I personally like method 2 better than method 1 because I feel like overall I do fewer steps. But if you want to try method 1, just know that as long as your answer matches mine, you did method 1 correctly. So method 2 says first find the least common denominator of all the fractions in the problem. So I take the first fraction, denominator T. I look at the second fraction, denominator S. I do not have it, so I need to include it as a factor of my least common denominator. And now I'm going to multiply this complex fraction by a special form of 1. And that special form of 1 is going to be T times S over T times S. So I'm going to put it all in one fraction. 1 times T times S, 1 over T plus 1 over S times TS. Notice I need to distribute inside the parentheses in the denominator. Numerator is TS. Denominator 1 over T times TS, 1 over S times TS. I can cancel common factors. In canceling the common factors, the denominators completely go away. So we've reduced that complex fraction into a regular rational expression. And the numerator is still the same, TS. The denominator, I have S plus, and that is the simplification of that complex fraction. Part B says to evaluate the formula when T is 250 and S is 100. So let's plug those in. We have TS over S plus T. T is 250, S is 100, and multiply on top, add on the bottom. 25,000 divided by 350. We can pull up those calculators and get our calculators working for us. And the calculator will return 71.42857, lots of numbers. What do we round to? Well, the problem tells us to round to the nearest 100. 100 has 2 zeros, so I need 2 decimal places in my answer. And a reminder about rounding, I want to round to the 2, so I look to the next place to the right. 8 is 5 or above, so this 428 is closer to 0.43 than it is to 0.42, right? 8 is higher, so it is closer. Remember, rounding, we want to get close values. We want to round to the closest or to the nearest. And so this would round 71.4 because the 8 is higher than 5 or bigger. I'm going to round that 2 up to a 3. Now, the problem tells us what units we need, but it's a little bit hidden and obscured. Resistance is in ohms, so this is in ohms, 71.43 ohms. And remember, for solving word problems, application problems, you want to make sure you attach units to the number or a description so that anyone reading your work will know what that number means. And there you have complex fractions. Happy studying!